A lot for being here as part of the reset stage at CogX. Come down from Cambridge this morning. So I'm really happy to be here presenting, representing Cambridge and the Turing. So even though I'm actually at the Department of Physics in Cambridge, my work is in theoretical machine learning. I work on models like Gaussian processes, which are really powerful non-parametric machine learning tools for conducting regression, classification, time series modeling, and the such. So the aim of this talk is really going to be to give you a bit of a flavor or an essence of how Gaussian processes actually work and what is the meaning of learning within the framework of a Gaussian process. So for the purposes of this talk, we assume the standard regression setup because I think that's ubiquitous and it's everywhere and everybody kind of understands the idea of conducting a regression. So we have our X data and we have our Y target or output variable, which we want to model. Our X is the input data, which is usually considered fixed. And the idea about regression is to really find the causal link or the mapping between X and Y, which is the function f, which is unknown. And this is really the primary objective of our sort of model fitting process using a Gaussian process. So we consider Y to be a noisy target variable with some additive Gaussian noise with a mean of 0 and a variance of sigma square. So the traditional parametric approach to the regression problem is to select a functional form for your model at the beginning of the learning process. So when we have our data, like these examples of just simple one-dimensional toy problems, where we can actually visualize the data so we can actually tell whether we want to fit a linear model to it or we want to fit a polynomial, a quadratic, or a higher order polynomial. So this is like the standard parametric approach. Learning in the parametric approach means just inferring the parameters once we've already decided on the functional form of our model. And this is how a lot of people go about doing regression. Gaussian processes actually offer an alternative way to solve this regression problem. It offers a non-parametric way. And I'm going to spend some time talking about what it actually means for a model to be non-parametric rather than parametric. So we've seen what is a regression problem. It's about finding a mapping between some input variables and your target output variable, which is a random variable. And we're going to talk about what does it mean to be non-parametric, and then eventually what is a Gaussian process and how it's used to actually solve the regression problem in a non-parametric way. So one of the things, okay, that equation is a bit messed up, but so the most important thing about the non-parametric approach is we don't start by selecting the functional form of our model. We essentially don't know it, and we don't impose a functional form on our model. We just say, we don't know what the functional form is, so the task of the learning in a non-parametric model does not just apply to learning the parameters, but also learning what could be the functional form of the model. So this phrase, letting the data speak for itself, is commonly used to describe non-parametric approaches in machine learning. What that really means is that the parameter set in a non-parametric model is actually not fixed. It's fluid. It could grow with the size and complexity of the data. In other words, it adapts to the data as more and more data becomes visible. So the learning in a non-parametric context applies to both, first, learning the model structure or learning the functional form, and once we've done that, to then learn the parameters of this functional form. So we can now start talking about what is a Gaussian process. So as the name suggests, it's related to a Gaussian distribution which is fully characterized by its the first order, the second order moments, the mean and the variance. The mean is just the peak value, and the variance governs the spread of the distribution. So a Gaussian process is a generalization of a Gaussian distribution. So the way I like to think about a Gaussian process is in terms of sampling. So when you sample a Gaussian distribution, which is one-dimensional, you get a scalar value. So you get a value x, which is a scalar. Gaussian distributions you can have high-dimensional Gaussian distributions. So when you have a bivariate Gaussian distribution, when you sample from a bivariate Gaussian distribution, you actually get a vector of 2 values. Similarly, when you sample from a k-dimensional Gaussian distribution, you get a vector of k values. So far, so good. A Gaussian process is slightly different. When we sample from a Gaussian process, we don't get a vector of finite length. We think of it as sampling functions directly. So a Gaussian process is actually a distribution on a space of functions. So because functions, mathematical functions, are defined on a continuous domain, one can actually think of a function as a vector of infinite length. And Gaussian processes actually define distributions over such space of functions. And hence, sometimes they're actually called infinite dimensional analogs of the standard Gaussian distribution. So this slide is kind of meant to give a little bit more of that insight. So what we see on this graph is actually 20 random samples from a Gaussian process. So each curve there is a function that is sampled from a Gaussian process. And exactly like a Gaussian distribution, a Gaussian process is parameterized by a mean function and a covariance function. It's the covariance function which is the key ingredient in constructing a Gaussian process. The covariance function, k, actually governs different properties of these functions. So, for instance, this example here is of samples drawn from a Gaussian process which have something called the RBF kernel function. And this kernel function has hyperparameters like the length scale L, which appears in the denominator. It actually governs how quickly our functions change. But because it's an RBF kernel, it's smooth and it's infinitely differentiable at any given point. But essentially the key idea to understand is that the covariance function encodes the structure of the functional form, which defines the space of distributions in the Gaussian process. So these are some examples of samples drawn from a Gaussian process for different types of covariance functions. And so this one is the RBF covariance function, which gives you these functions which are really smooth and they have some periodicity. The length scale governs how quickly the bumps decay and come back up. The center graph is from a Brownian kernel covariance function. So we can kind of start to see, by modeling spaces of functions in this way, we can start to associate with real-world data what type of kernel functions we are looking for to encode our structure. So when we think of like stock price returns, they very much look like the kind of samples drawn from the center graph there. They're really noisy and jagged lines. The final graph is of something called the Mattern covariance function, which is not smooth, but it kind of combines properties of the Brownian kernel and the RBF kernel. So I think this is a really important graph to give like intuition about how Gaussian processes work. So the main idea is that Gaussian processes define distributions over a space of functions. And how these functions look is something we completely control by deciding on what kernel function or what covariance function we choose. So then the key question is, okay, so that's fine with what a Gaussian process is conceptually. It defines a distribution over a space of functions. But then how is it really useful for regression, where we want to find a mapping between x and y. We have some noisy data points, and we want to find a function that passes through them. The interpolation problem, which is, appears in almost any field where we have an input and an output, and we want to understand how they're related. So in this graph, what we see is the space of sample functions that we define our Gaussian process to have, and we select the RBF covariance function, so we get these smooth functions. And then we observe some data points. And how regression works in a Gaussian process model, just intuitively speaking, is once it observes the data, and once the data starts coming in, it filters out all the functions that don't pass through the data or don't pass next to the data. And in that way, it just preserves the functions that pass through our data points. And this is kind of how it solves the interpolation question about finding a nice curve that passes through our data or passes close to our data. So the final graph has these gray bands, which are really interesting. So what the gray bands tell you is they capture uncertainty in our predictions. So for instance, we have our data points at several different sort of parts of the X line, and we have regions where we don't have data. What that really means is that the Gaussian, when you fit a Gaussian process model for regression, it will actually tell you regions of your training data set where you don't have enough data to make a confident prediction. So those gray bands there can be interpreted as a measure of confidence. It's actually the standard deviation of all the functions that pass through our data. So if you observe on the second graph there, the part between 2 and 4, we don't have a lot of data. So the functions have a lot of leverage to move around quite a bit because we just don't know, we just don't have data in that region. So as long as the functions pass through the data points, they can actually vary a lot in parts where there is no data. And this is exactly what's captured in the uncertainty bands in the final graph. So in a way, this is very different to the parametric world where we say, okay, I have some data and I'm gonna solve this regression problem by actually selecting at the outset a functional form. In a Gaussian process world, the inference takes place directly in the space of functions rather than figuring out a functional form and then going about inferring or learning the parameters. So the learning or the inference happens directly in the function space. So, oh dear. So this is just a slide to convey mathematically how this process of going from the prior to the posterior works. So one can think of a prior as a distribution and the posterior as another distribution. And what we are trying to do is just trying to go from the prior distribution to the posterior distribution after we observe some data. And now because we operate in a Gaussian world and all our distributions over our functions are all normal, this is a completely tractable mathematical problem that can be derived analytically. So the process of going from the prior distribution, the prior probability distribution of functions, to the posterior probability distribution over functions, which is actually a conditional distribution because we observe some data. Given we observe some function values, what is our probability distribution over the rest of the function values? So this is a really simple operation mathematically. It essentially starts by, the brackets, the R over there is actually just a bracket. So there's only 2 steps in going from the prior distribution to the posterior distribution. We have a joint Gaussian distribution, and once we've defined our joint Gaussian distribution, we just go from the joint Gaussian to the conditional Gaussian using the rules of manipulating Gaussian probability distributions, which is very, very standard. So this final equation there is actually the prediction equation. The first part is the mean, and the second part is the covariance matrix of our posterior distribution. So we can see that all of this is absolutely tractable. Like this is a closed form derivation of a posterior distribution, which is really one of the amazing properties of using a Gaussian process model, because it assumes that our distribution over functions is Gaussian, hence we can exactly derive our posterior distribution. The K there is the covariance matrix, and the important thing is that if you look at the mean and the covariance carefully in this equation, we see that it involves inverting the covariance matrix. Now this is the main catch about using Gaussian processes, is that they're computationally quite expensive because we need to do the operation of inverting a covariance matrix, which is of size n by n, where n is your number of data points. And standard computers start to sort of have problems inverting matrices above 1,000,000 points. So it's really a question of when can one use a Gaussian process model is when we want to fit our complex data in a sophisticated and a non-parametric manner, but at the same time we don't have an explosion where we don't have tens of millions of data points, because then we need to think of all ways to tweak our Gaussian process. We still want to use a Gaussian process to kind of make it work. So the key benefits are it gives you solid uncertainty predictions. The fact that you can actually choose kernel functions to encode the shape of your functions gives you a lot of flexibility. So if you have one-dimensional data, potentially you can just look at the data and you can say, okay, I see a periodic component and I see a linear trend and I see a flat line here. So you can actually construct kernel functions that encode all of the properties that you want in your data. So my research is actually about how do you select kernel functions once you've decided that you want to use a Gaussian process model. The kind of approach to selecting kernel functions for your Gaussian process right now is quite heuristic. There are no proper rigorous ways that tell you that, okay, once you have your data, you conduct these manipulations and then you can figure out what kernel function. It's really trial and error sometimes, or it's about constructing your kernel function by trying to geometrically analyze your data, trying to, basically, it's basically a lot of trial and error. So mathematical tractability is the other key benefit of using a Gaussian process model. You don't need to resort to any type of sophisticated approximation stuff. You derive your posterior distribution straight away. The drawbacks is that it's quite expensive to train, so one needs to kind of think about what types of applications a Gaussian process model could actually be useful in. And there's no rigorous way of choosing the kernel function. So my research really lies in that area. So as to how do you go about actually constructing kernel functions, and how do you capture different properties? It's like structure discovery. How do you capture different properties in your data and convert them into a mathematical form in your kernel or covariance function? So I'm going to just finish with some applications. The one that's most interesting to me is in particle physics. So where Gaussian processes are used to model densities of a mass of a particle, and these particles can be unknown, they could be exotic, and we don't know if such particles exist. We just accumulate a lot of data. So in kind of estimating the density in such context, Gaussian processes are really useful because they're totally non-parametric. They don't assume anything about the functional form of your data. So they are used a lot in finance and econometrics as a tool for time series modeling, and it's kind of easy to see why it could be an attractive tool for time series modeling, because you can encode different shifts in regime in your data when we're looking at time series. They're also used in a host of other fields. I have this one example where a Gaussian process model was used for regression. in order to actually capture the average daily maximum temperature. And so this example is particularly useful to understand why Gaussian processes are useful. So when we look at weather, we kind of know that there's a periodic aspect to it. So we can actually modify our kernel function to encode that periodicity in our kernel function. And we kind of know that the temperature goes up during summer months and then it comes down during winter months. And this kind of periodicity and the shape and how quickly the bumps come down, et cetera, can all be encoded in the covariance function of your Gaussian process. And so that's really interesting to me, is to actually look at data in a completely non-parametric way, to not assume any functional form of your data, and to just let the data speak for itself, basically. So yeah, I just included this graph because I think it conveys why the idea of selecting the right kernel function is such a challenging problem. So in the one-dimensional case we saw here, we have the aid of visualizing the data, so we can just visualize our data, and we kind of know that, okay, there's periodicity, and you know, it has this dynamic aspect, it goes up and down. But in high dimensions, we kind of lose that ability to geometrically understand a data set. It's much, much harder in high dimensions. So this is an example of GP regression, but where instead of fitting a curve, we have to fit a surface, because we are in our X has 2 dimensions. So we have X1, X2, and then we have Y, which is our target variable. So what we actually end up getting is a surface that passes through all our data points. So yeah. That's the end of my presentation. Thank you.